2410, 2410. Maximum matching of players with training. I just did this problem. I think it's pretty approachable, and I thought I would just articulate an easy way to solve it. Apparently I can't click over here. Oh yeah. Alright, so let's get right into it. So you're given a zero index integer array players, where player's I represents the ability of the ith player. Okay. You're also given a zero index integer array trainers, where trainers j represents the training capacity of the jth trainer. The ith player can match with the jth trainer if the player's ability is less than or equal to the trainer's training capacity. Additionally, the ith player can be matched with at most one trainer, and the jth trainer can be matched with at most one player. Okay, return the maximum number of matchings between players and trainers that can satisfy these conditions. All right, so in this example, we have, players equals 479, and we have trainers equals 8258. Well, we can match player 4 with this trainer, or with this trainer, or with this trainer, right? Because the trainer's capacity is greater than or equal to the player's capacity, right? So 7 can be matched with this trainer and this trainer. 9 can be matched with 0 trainers, right? Because there's no trainer that has a capacity greater than or equal to 9. So this problem, you kind of have to have the intuition to think that, okay, there's probably a greedy solution to this problem. Because when you look at a list of trainers, if we sort the players, right? If we consider them sorted, since there's this issue where a trainer can only be matched with one player and vice versa, right? There's only one-to-one matching between players and trainers. We kind of want to maximize utilization by, seeing if there's, for all the small trainers, try to match them with the smallest players, right? So like, if you were looking at this guy, right, if you want to get a small trainer out of the way, then only consider smaller players. You only want to look at players that are smaller than this guy, because it doesn't really matter like who matches with who. So the idea is to greedily do this in order, because we're just trying to maximize the number of people that we get trained. So if we're looking at something like, is there another example? If we're looking at something like 2, we're just trying to match 2 with somebody and increase the score by looking at players that are less than 2, right? That's not going to affect any future players that have capacity greater than 2, because they'd never be able to match with this trainer 2. So we can just greedily decide to match players with this trainer. If a player exists that's less than 2, it's not going to affect, right? It's not going to create what I'm trying to get at is it's not going to create a situation where, you should have matched this trainer with somebody else because that freed some other player to train with somebody else, right? That kind of situation won't arise, because if you have a trainer with 2, it's only going to affect players that are less than 2. So the idea for this problem is to look at the trainer and look at the current player and say, well, for this current player, what trainer can match them? Now, since this is sorted, these are both sorted, if a trainer can't match the player that I'm looking at, it's not going to be able to match any subsequent player, right? So if I'm the least capable player and a trainer doesn't match me, it's definitely not going to match any player after me, because every player after me has a larger capacity, right? Because I'm the lowest. So when I look at player 4 and trainer 2, and I say, well, this trainer isn't going to match for me because it doesn't, its capacity of its training capacity of 2 is less than my capacity of 4. And it's definitely not going to match any of my subsequent players because they all have values greater than my own. So this goes away, right? And then we look at 4, right? Well, this is where it gets a little tricky, right? So, 5 will match for me, right? 5 will match for me. Now, will it match for my subsequent players? Maybe. Maybe it will, right? But the subsequent trainers are greater than me. So the subsequent players are greater than me, and the subsequent trainers are greater than 5. So any subsequent trainer will be a better match for the subsequent players than this one is for me, right? Because I'm the smallest player, and this is the smallest trainer remaining. So this is the best match for me because any player that's left is larger, and any trainer that's left is larger. So this is the smallest difference between player and trainer, right? We're trying to match people up according to their size. That's another way you could think of it, right? You're trying to get everybody to match up that they have the most similar size. You don't want to match me with someone bigger than the minimum trainer that can match me because that bigger person could be better used for a player that's bigger, right? So that's another way of thinking of this problem. Kind of intuitively, you can kind of think that the optimal solution would be to minimize the difference between players and trainers, right? Because if I can be used by something that's small, it only gets worse if I get used by something larger because a subsequent player may need something larger. So that's the general idea. So if I have this 4 and 5, okay, well now 4 and 5, this works. So I add 1 to my ledger and I remove 4 and 5. Then I look at 7, I do the same thing, okay, the same. So I add 1 to my ledger and I remove 7 and 8. I look at 9 and 8, I look at 8, 8 doesn't work, just 9 left, and that's it. So my ramblings at the beginning were pretty bad, but I think that I was able to make an explanation that kind of makes this make more sense. So let's just go ahead and, so we'll have a number of solutions. Let's call it res, because that's what I've seen a lot of really cool people do, I guess. So res equals 0, and then we're going to sort players. Now we're actually going to do that in reverse. That way we don't have to deal with pointers. We can just kind of pop things from the back and process it that way in constant time. And we're going to sort trainers. All right. And then what we're going to do is while there's players and while there's trainers, sorry, why do I always do that? And while there's trainers, right, so while there's players and trainers, we're going to get a player and a trainer from the top of the list, or the stack, I guess, right? And what happens is, well, while there are still trainers left, because we're trying to match this player, right? While there's trainers left, but the trainer's value is less than the player's value, right? So this trainer can't accommodate this player, and since they're sorted, this trainer can't accommodate any subsequent player. So if it can't accommodate me, it's not going to be able to accommodate anybody else, so I need to try the next trainer. And trainers pop again. Right? Now, if we get to the end, then either we ran out of trainers or we found a trainer that can accommodate us, and it's the best trainer to accommodate us because it's the minimum trainer remaining, right? Because the trainers are sorted. We'll say res plus equal trainer's value, because we always have at least one trainer, right, is greater than or equal to player. And then we return res. Let's run that. Sorry, I'm kind of tired today. All right, cool. And then what's the runtime of this? Well, we'll call P, say, let's just make this a big comment. Okay, so P equals the length of players. And we'll say T equals the length of trainers. To sort players, that's P log P time. To sort trainers, that's T log T time. And then we look at each player and trainer. So we pop each player and we pop each trainer. Let's see, we only pop a player once, we only pop a trainer once. So you're never going to redo an operation, so it's an additional P plus T time. So the runtime is P log P plus T log T plus P plus T. All right, everybody, have a good day. Thanks.